Okay, so make sure you have your calculators today. Of course, there's always one. All right, so we talked about the standard normal curve last time. And the equation for the standard normal, well, first of all, the equation for that was e to the -1/2 z squared where z was defined as the distance between an individual value and the mean over the standard deviation. Now, before, the standard deviation was for the standard normal curve, the standard deviation was 1. And then this was over the square root of 2 pi. Okay, so this could have been rewritten as all right. Now, we also talked about the fact that this was kind of a parent function because not everything has a mean of 0 and a standard deviation of 1. Okay, standard, and I'm just going to put that in here. The average, which is the same thing as mu, is equal to 0, and the standard deviation was 1. All right. Now, in order for us to modify this so that we're able to deal with, changes in this, okay, we have to reintroduce the sigma notation back into z because it won't always be 1. But also remember, this was 0. Okay, yeah, I guess I could have cleaned it up even further. That was 0 for the standard normal curve, which reduces even further to negative x sub I squared all over 2. So we're going to have to put all of these pieces back in to deal with something that is not a standard curve, but is a normal curve. So here now we have e to the -1/2 x sub I minus mu, or x bar. And we see that we have a standard deviation in my denominator here. Okay. This effectively spreads out and draws out the curve, and allows me to have a very small standard deviation or a large standard deviation. Remember, a small standard deviation looks like a very tight little tight little hat right there, whereas if it's big, it's kind of more smoothed out and is shorter, because remember, the area under both of these curves is 1. Okay, so normally this was 1 up here in the standard normal curve. All right, so we didn't see it because it was just a 1. But if my standard deviation is smaller than 1, okay, if it's smaller than 1, it's going to cause this to become bigger. My numerator is going to become, well, my total value is going to get larger because my denominator is now smaller, which increases the height. Whereas if my standard deviation is big, that means I'm spreading it out over more, and my total value decreases, and that's why it's a smaller height. Okay. Now, 99 times out of 100, you're not going to have to compute this. But I do want you to see it so that if you ever do have to see it, you know what to do with it. All right. Now, let's do some problems. All right. So let's say I have a average of 1.01, a standard deviation of 0.02, and I am particularly interested in the value of x equaling 1.03. Okay. Now, if we go to our calculators, now, by the way, if you go to second distribution, you'll see that numbers 1 and 2 are normal PDF and normal CDF. I will tell you this right now, you do not need number 1, ever. The only time number 1 is used is when you're graphing. Because what normal PDF is saying is, remember what a PDF was. It was a particular density function. It was one particular value. So let's think about this. If I have a continuous curve and I am interested in the probability of an event occurring like this. So let's say, for example, I'm measuring the heights of a certain species of bush, okay? And I'm measuring all of these little shrubs, okay? And they have an average height of 1.01 meters, okay? And the standard deviation of the heights of these shrubs is 0.2 meters. So these shrubs pretty much all look alike. What are the odds if I were to walk up to a random shrub? What are the odds that it would be exactly 1.03? Well, take a guess. What do you think? Forget about the calculator. Don't even use it. But think about that. What is of all? And because remember, I have heights of all values. You know, I have some shrubs that have a height of that. So what do you think the odds are of me getting one that is exactly 1.03? With no other decimals. Perfectly. 1.03. Well, let's ask ourselves the question. What are the odds of me getting a shrub that is greater than 1.01? Forget about the calculator, you don't need it. What are the odds of getting one that is above 1.01?
50%.
50%. 50%. Okay, good. And we talked about those magic numbers at 68%, 95%, 99.5%. But I'm not talking about a range of values. I'm talking about a specific singular value only. How about this? Let me ask you this question. What do you think the odds are of me measuring my shrubs and I get one that is that? What do you think the odds are of getting that exact height?
4%.
Because you went into PDF, right?
No, I just guessed.
Guessed? Good, because guess what? That's wrong. But it's okay. All right, but let's use them as, do you think it's bigger than 4% or smaller than 4%? I'm telling you it's not 4%.
Extremely smaller than 4%?
Is it, I'm sorry, say that again, please.
I don't know. If you said that you have all the values and you just get a really specific number, if you have everything, then
Yep.
it'd be really small.
And what if I wanted to have one that was that for my height?
Even smaller.
Even smaller. So why does everyone wonder about that being any different than that? Think about that for a second. Exact height. Let me ask you this question. How thick is that line? In mathematical terms, how thick is that value?
One-dimensional.
And how thick is something that is one-dimensional?
Infinitely thin.
It has no thickness. It is infinitely thin. Yes, it has 0 thickness. So the probability of getting one exactly at that one particular height is 0. Let me ask you an interesting question. For those of you who just might want to think about this for a moment. Don't think about it too hard because I want you to think about other things. Let's say I have a sphere. It's about this big. And 2 flies land on it. Random locations. What are the odds that they land in opposite hemispheres? There's no markings on it. It's a perfectly smooth, unmarked sphere. Has no markings on it. A fly lands one place, and then a moment later, a fly lands somewhere else. Think about that. So here we have mu is equal to 1.01, sigma is equal to 0.02, and x 1, which is the only one that I care about right now, is 1.03. Okay. Okay. So looking at my distribution here, I'm interested in the normal CDF. Okay, now normal CDF is cumulative. All right. And I am interested in everything from here on down. Now, believe it or not, you can solve this problem without a calculator, but that's okay. We'll do it with it. So my lower bound is going to be, because I want everything from here over. So that means my lower bound is going to be basically negative infinity, -1 times 10 to the 99th. My upper bound is 1.03. My mu is 0.02, and my sigma, my mu is 1.01, and my sigma is 0.02. And it spits out that probability. Remember, give it to me with 3 sig figs, please. Okay. Now, you're lucky that you have these calculators. By the way, you can do this without actually doing the calculator, although it's a little bit less accurate. What is the z-score for 1.03? So how many standard deviations away from the mean is 1.03? Well,
One.
yeah, z is equal to the one individual value minus the mean divided by the standard deviation. So if this is at 1, okay, that would tell me that, first of all, everything over here, if I'm just going to redraw this, if this is at 1 standard deviation and I want everything below it, remember that between 1 standard deviation above and below is 68%. This is 34, and everything from here on over is 50. So 84%. And that's just doing it using the ballpark estimates that we learned the other day. 68% is in here, so that must be 34, and everything over here has to be 50. So the grand total, 50 and 34 gives me 84, and we're doing it by the calculator gives me a little bit more significant digit here, and gives me that smaller resolution. All right, now, okay, so that's fine and wonderful, and everybody's excited and happy. I can tell. Wow. Jacob's jumping up and down. I think I saw Herminia do a cartwheel.
How'd you know?
Dude, I can see you. The other kids in the class can't see you, but I can see you. Yeah. Now, here's an important question. Let's say I make widgets. And my widgets are on average, they weigh 7.34 kilograms. I have a standard deviation of 30 grams. When the widgets get extruded into their containers, they are weighed. And I want okay. So in my widget factory, I've got these dimensions that I know. And I want to get rid of the lowest 5 percentile. Now, this is an interesting point. What the heck is a percentile? A percentile is what happens when you rank things. So if we look at, say, somebody scoring in the 80th percentile of something, that means they are better, bigger, faster, stronger, smarter, whatever, than 80% of the people who took the test. Okay? So it's a ranking system. So I want, if I'm thinking about this visually, I've got my average, I've got a standard deviation, and I want to find out where the lowest 5% is. Because I want to calibrate my machine to say, if you are below this weight, you are too small, you're a reject, you're out of here. Okay? The question is, what is the minimum weight that I'm going to allow to survive my sorting machine? Okay? So in this situation, I'm kind of getting it reversed. I want to find out what value is x sub I so that the area is 5%. So before, we were able to figure out the area by using normal CDF. We were able to say between this value and this value, how much of the curve is there? Well, now we're asking you, I want this much of a curve. What value should it be at? So now this is a little different, and I'm going to introduce you to a new function. Go to second distribution and go down to number 3. Okay. Now they're asking you the area, and we're going to go, let me walk through these commands. The area is 0.05. The average, what is my average?
The 7.34.
Okay. What is my standard deviation?
0.03.
Good. Now they're asking you for the tails. So I'll walk you, left and right are pretty much the same. Right is when I'm looking for these guys over here on the upper end. Left is over here. Center is when it's evenly spaced on both sides of the mean. Okay. And paste. So I get a number. What does that tell me?
Anything that's 7.29 kilograms or less is rejected.
Correct. This is the weight. Now, by the way, it did say, now just to be like playing the devil's advocate here, to go back to the problem that I talked about before. If an object goes through my scanner and it comes out to be that weight, do I accept it or do I reject it? Right? First of all, that's never going to frickin' happen because the odds of it being exactly that weight is 0. So that's why we just say, you know what, to hell with it. We're just going to have a couple of digits here because I can actually weigh that many kilograms and we're good. But unless you're pulling out a super sensitive scale and you're measuring down to the microgram, you're not going to get this kind of weight. Okay. All right. So, let's do this. Now, same widgets. But I am going to cheat my customers. And anything that is in the top 10% of weights, I steal for myself. My collection. Because not only do I make widgets, I collect them. What is the smallest item in my collection? Put your answer in the private chat and make sure it has 3 sig figs, please. So I'm getting all sorts of permutations of bad rounding. Okay, so let's deal with this. What I'm looking for is this area to be 10%. So I am looking for the x sub I value that gives me that. So that's an inverse norm. So second distribution inverse norm. I want my area to be 10%, so 0.1. And I want a right-handed curve. And so 0.1, sorry, 7.34, 0.03, right. And that gives me 7.38 kilograms. Okay, so some of you are telling, I've got more than one person telling me in the chat that your software is different than mine. That is fine. Okay, in order to pull it off, let's say it doesn't give you left, right, or center. Okay. Then you're going to do this. Inverse norm 0.9, because it'll automatically give you left, and it'll give you the same value. So if your software, if your software version isn't like my software version, that's fine. You just might need to change your boundary conditions. Okay. All right. Now, let's do this. Um, so my cousin Ralph, who I don't like, wants to buy my company, but he wants a good sample. He wants to know like what is an average widget. But you see, if I give him an average widget, that's not nearly as impressive as a very big widget. Big widgets are better. So I'm just going to give him a sample from this window of 66 to 70%. Because if I give him a sample from that, he's going to think that's the average. And he's going to be like, wow, you make really good widgets. And he's going to give me a really big price. Remember, I'm crooked, right? I already told you that. So I'm going to cheat my family. Remember, I think it's the 34th rule of acquisition. Never let family get in the way of profit. So now we have to find out what these values are. What does the 66th percentile look like? And what does the 70th percentile look like? This is not going to be done in one fell swoop. You're going to have to do this in different parts. So, can anybody help me in my my problem?
Well, if you're looking for the maximum and the minimum, you could carry out two calculations to find the sizes for what's the 66th percentile and what's the 70th percentile, and that would give you your range.
Right. You want to do a calculation for this, and you want to do a calculation for that. This is not one calculation. You're going to have to do this, run this calculation, and then run this this calculation. Do both of them. Some people do know the rules of acquisition. Thank you, Herminia. Rule 34 is war is not good for business. War is good for business. That is right. And I think 35 is occasionally declare peace. It confuses your opponents. Something like that. For those of you that are Star Trek fans. Solve this problem, not the Ferengi problem. Yes, always give me your answers to 3 sig figs. Good. A lot of you guys are getting the right ones here. Some of you, I think, are might be putting in like calculator errors. But I got 7.3. I'm going to put more digits in here. 237. You can just, and as I told you, round it to 3 sig figs. So that would be, but I'm just putting it in there so in case anybody might have typed it in wrong, they'll know. Which is 7.36. Okay, good. Now, and I'm going to ask this one to 4 sig figs. So I got busted. He sued me. The judge threatened me. And now you're my factory operator. And you got to figure out what are my min and my max if I'm going to take the sample from the middle. Hmm. Interesting. All right, so if you've gotten it right, I've told you, yup. But if you've gotten it wrong, I didn't respond. So let me just remind you where we're looking. On the last problem, I was stealing between 66 and 70%. So I was stealing 4% of the whole sample. Okay. I need my amount to be from the middle. So that means I need 2% on this side and 2% on that side of the middle. Okay. Good. Getting the right answers now. All right. So, all right, good. Some people have rounding errors. All right. Everyone's gotten the right answers now. Even if I haven't answered you, everyone's gotten the right answer now. All right, cool. Awesome. Okay. All right, so now let's do this. My other business is selling doohickeys. The standard deviation for my doohickeys is 0.01, and the length of a doohickey is 138 miles. They're very big doohickeys. Okay, I think I've answered everybody who's answered. Okay, so this was a binomial, sorry, not binomial, this was a normal CDF. My upper was 139.05. My lower was 138.03. My mu was 138. Standard deviation 0.01. And the number that spat out at me was 0.0013499,672. I want 3 sig figs. These, okay, just for those of you that are having issues with sig figs, these leading zeros are not significant digits. Those are the first 3 sig figs. And so I'm going to round this to, and if you converted it into a percentage, it's 0.135%. I make very good doohickeys, even if they are 138 miles long. Should see the warehouse. It's impressive. All right, cool. Let me see, what else have we not covered? Oh, look at that. Um, so I have 2 kinds of doohickeys, full flavored and diet. And I select 10 doohickeys. One at a time. Because you really can't hold more than 1 doohickey at a time. I mean, they're 138 miles long. And you sample it. And then I will say that I have, by the way, let's say I've got 12 million in my factory. That's not how you spell warehouse. Okay. Oh, and I will say, wait a second. I will say that 30% of my sample of my stock is diet. Because if you're eating anything that's 138 miles long, you're not on a diet. Now, what are the if I take 10 doohickeys, what are the odds? What is the probability that 3 are diet? That only 3 are diet. And of course, give me your answer to 3 sig figs. That's all the answers I'm getting? Nobody else is answering? Okay, so what kind of a distribution is this? What
Binomial.
command should I be using?
Binomial PDF,
Why is it a PDF?
because there's two,
Okay,
the diet and the full flavor.
okay. Why is it binomial? I'm not saying you're wrong. I already told you in your answer that you were right. Why is this binomial though?
The multiple trial.
Multiple trials, that's one of the criteria. What are some of the other criteria for a binomial? Perhaps the most important one.
Oh, isn't it? There's only two possible outcomes.
That's another very important feature. Yes, that's also in the list. There's another one.
Percentage.
That they have to be independent trials. They have to be independent, meaning that if I flip a head on the first coin, it doesn't affect the odds for the second coin. Now, let's say I had 20 doohickeys and I selected 10 of them. And as soon as I selected one, I ate it. Would that be independent? No. But what if I put it back in the bucket? It's a very big bucket. Then it would be independent because I could theoretically choose it again. And this is why I said, well, first of all, let me ask you, is this an independent experiment? I see Emma nodding her head saying it is independent. Why is this independent? Even if I eat my doohickey.
Because of the sample size, it's so big.
Yeah, you know what? Changing the denominator from 12 million to 11,999,998 is not going to affect the result of this. So even if I take a sample and I eat the sample, whether I'm on a diet or not, the point is that it's not going to affect the odds of 30%. Okay? So that's important. Okay? All right. Because whether they're independent or not will determine what those odds are. Now, let's say I did have a sample of 20. Okay. Let's do this and say instead of having 12 million doohickeys in my warehouse, I only have 20 doohickeys in my warehouse. And I said that, well, now if I only have 20 doohickeys, how many of them are diet?
Wouldn't it still be 30%?
So how many are there?
6.
Wait,
Yeah, if I have 20 doohickeys,
30%.
30% of that is going to say I'm going to have 14 full flavor and 6 diet. Okay. Now, if I take one out and I'm picking 10, right? Now we're not actually going to compute this number. We're just going to like set it up. Okay. What are the odds of me pulling a diet on the very first pull?
.3.
Sure, or let's leave it as a fraction. I have 6 out of a total of 20. And I want to do that 3 times out of this whole thing. So this is going to be 6 out of 20, and then I eat it. So now it's 5 out of 19. And then 4 out of 18. Okay. Now, the next one is not a diet. It's a full flavored. I still have 14 full flavoreds in here.
Wouldn't it start at 14 out of 17?
Oh, snap. I hate it when you're right, Emma. She's right. Now I gotta fix them all. It's like the first rule they teach you in teaching school is never let the kids be right. That's really not true. That's the 6th rule. Okay, that's a 1. Okay. Okay. And if I were to actually multiply these out, or at least simplify them, would that be my answer? Well, let's think about it this way. This is an interesting point. This would just tell me the odds of me getting 3, right? Do I care about order in this? No, I do not care about order in this. So theoretically, all I would have to do is just multiply them across. If I cared about order, it would become a different kind of problem, because then there would be 3 ways of permuting these and 7 ways of permuting those. And I would have to deal with that. But just for giggles, let's just simplify. I mean, you know, some things do simplify nicely. And that one and that one. And that one and that one and that one and that one and that one. And then that one and that one and that one would take that down to a 9, which cancels with that one. And I would have 1 all over 19 times 17, and 19 times 17, don't tell me, that's 81 times 4, 330, 324 minus 1, so 1 over 323. Yeah. Yeah. So depending upon the problem, you will either use, let's think about all of our tools. What are our tools? We can use a line diagram like that. We can use the Binomial PDF. We can use Binomial CDF, which is this guy plus another guy, which is, you know, everything below it or everything above it, whatever. I can use normal CDF, and I can use inverse norm. Normal CDF is when I'm looking for a percentage given a value. Inverse norm is when I'm looking for a value given a percentage. Oh, snap, I just ran over time by like 2 minutes. I apologize. Okay, but perhaps you might want to ask yourself, why is it that I'm spending time at the end of class going over old stuff and putting it all down in a nice, happy way? Hint, hint, wink, wink. Merry Christmas. Go play in whatever is left of the snow. Have a great day, everybody. I'll see y'all later.
Thank you. Bye.
Thank you.
Good day.
Good one.
Bye-bye.
Bronco.